All right, everyone, we are going to pick up on section 6.4, and this would be page 46 of the notes, or page 55 if you look at the right-hand numbering. All right, so we're going to shift gears to what we call sampling distributions. And the idea with sampling distributions is that we know that when we take a sample from the population, we're only gathering information on a proportion of the population. So our sample mean might be different from what we're trying to estimate. Usually we estimate the parameter mu, which is the population mean, with the sample mean. And it's nice if that sample mean is really close to mu, but we know if we took another sample mean, it would be a little bit different. Maybe we've overestimated it, maybe we've underestimated it, but we know we probably didn't hit it exactly on the nose. And so we consider how much the sample mean would vary from sample to sample. And that leads us to the first definition here of the sampling distribution. So sampling distribution is the distribution of all possible samples from the population. So the sampling distribution is the distribution of a statistic, and it's the distribution of all possible statistics. So when I say statistics, I can mean maybe the sample mean or sample proportion. Okay, so that's the definition. It's a little bit abstract because we only go out and we take one sample from the population, but the sampling distribution you can think of as a histogram of all possible sample means from the population that we're interested in. Okay, and we're going to talk about what is meant to be unbiased. So I'll give you the definition of an unbiased estimator. And by estimator, we're just talking about something we use, a number that we use to estimate the parameter. Again, the sample mean is used as an estimator of the population mean. And an unbiased estimator is probably what you might think it is. It is when the mean of the sampling distribution is equal to the parameter you are trying to estimate. So you probably wouldn't have given that definition, but all that is really saying is that if it's unbiased, that on average, you're not overestimating or underestimating the parameter. So sometimes that your sample mean will be above the population mean, sometimes it will be below, but on average, it doesn't systematically over or underestimate the population mean. Okay, so we're going to talk about the central limit theorem. It is the most important theorem in statistics. We're not going to spend all that much time on it, but we need to know, before we can apply the central limit theorem, we need to know two things. We need to know, one, the mean and standard deviation of the population. And two, we need to know that we have a simple random sample. So we have a simple random sample. We oftentimes abbreviate this SRS from the population of size n. Our sample is of size n from the population. Okay, so the central limit theorem, all it really is doing is telling us something about the sampling distribution of x bar. Okay, so here we go. This is the central limit theorem. It can be applied to any population as long as the sample size is over 30. And it can be applied to a population where the sample size is less than 30 if the population is normal. So this first thing here is just telling us that the sample mean is unbiased. because the average of the sample means is mu. So this notation looks a little bit weird, but it's just saying that the mean of the averages of the sample means. So if you had many sample means and took their average, that's equal to the parameter you're trying to estimate. And so the sample mean is unbiased, not the sample. And here's this is telling us how spread out the X bars are. And it shouldn't surprise you that it's related to your sample size. So as your sample size increases, the standard deviation of the X bars will decrease. So it's related to two things. This is how much your X bars will vary if you took repeated samples and calculated X bar each time. So if you increase your sample size, you should have a much more accurate estimate of mu, and so you would expect less variation, and that's why it's divided by the square root of n. And then another important thing is that the distribution of X bars is normal. So this is very interesting since it's actually not required for the population to be normal, but we assume that the distribution of the X bars will be normal. And that's why we were able to do a lot of things we'll be doing in the next couple of weeks, is because of number 3. And because of number 3, we can apply this formula to calculate a z-score. So this formula is different than the z-score that you're used to. And it's different because we're dealing with the sample mean rather than an individual value. So you see X bar in the formula right here. And you'll see the denominator is sigma divided by the square root of n. Because we're dealing with X bar, I have to divide by the standard deviation of X bar. And we know from up here that's equal to sigma divided by the square root of n. Okay, so we have to keep that in mind. These problems are going to be a little bit different because we have a different formula. You can still use your calculator, you can still use the table, but they're different because we are dealing with the sample mean rather than an individual value. Okay, so we're going to work through a couple problems, and we'll start on the next video with the problems.